Hello, today we're going to talk about the mass spectroscopy of elements. Okay, so let's start talking about isotopes. Isotopes are the same element, so they have the same number of protons. It's always given on the periodic table. So let's look briefly at oxygen. Oxygen has an atomic number of 8, which means it has 8 protons. 8 protons, uppercase P for proton for the most part. So let's see. Isotopes will then have different numbers of neutrons. So you might have an oxygen atom that has 8 protons and 8 neutrons. You might have a different oxygen atom that has 8 protons and 9 neutrons. You might have another one with 8 protons and 7 neutrons. All three of these would be considered isotopes of each other because they have different numbers of neutrons, but they're the same element. Now, if you were to change one of these to, say, 7 protons, 8 neutrons, that changes the element. So instead of being oxygen, now it is nitrogen because it has 7 protons. So when we're looking at isotopes, they will have different numbers of neutrons, which means they will also have a different mass number. Mass number is always the protons plus the neutrons. It's always a whole number. So the mass number for this oxygen atom is 16. We usually write that after a dash. So oxygen 16, this one would be oxygen 17, and this one would be oxygen 15. So you've probably heard of like carbon 12 and carbon 14. That's where it's getting those names from. That's the mass number. Now we'll talk about the atomic mass in just a second, but the atomic mass is given on the periodic table. The mass number is not on the periodic table because it can change. Same thing with the number of neutrons, not on the periodic table because it can change. So there's a device called a mass spectrometer that helps us to measure those different isotopes of the elements. So what it kind of does is it's like a curved tube almost like this. And I'm simplifying it a little bit, but the heavier isotopes, because they're heavier, will not deflect as much, whereas the really light ones will go around the corner and be pulled around further. And then there's a detector, and it will detect how many isotopes are here versus here, for example. And again, that's a big simplification, but essentially what it outputs is the mass of the individual isotopes and their abundance. So we talked about oxygen. So oxygen, might have oxygen 16, oxygen 15, oxygen 17, or whatever they are. Most of the oxygen that you're going to see is going to be oxygen 16, maybe 95% or more. I don't know the numbers off the top of my head, but this is just an example. And maybe another 3% of the oxygen atoms are oxygen 15, and the last 2% are 17. So that would be, this is what we call the abundance. And of course, these are the isotopes. Now, since we're measuring an AMU stands for atomic mass unit, you're going to get numbers that are not exactly 16 or 15, 17. You're going to get decimal numbers in AMU. But if they don't give you the value at AMU, you can just use those mass number values instead, and that's okay. Let's go back to the periodic table. Each element will typically have 2 numbers given. The atomic number, which is the number of protons, and then the atomic mass. It's usually a decimal number because it is an average. It's an average of the different isotopes of an element. So maybe you have oxygen 16, oxygen 17, oxygen 15, whatever those different masses are, it's an average, but it's a weighted average based on the abundance or the percentage of each of those isotopes in nature. So what it looks like when you're calculating with average atomic mass, the first thing you would do is you would take the percentage of that isotope and change that into a decimal. We call that decimal the abundance. And then you're going to take those decimals and multiply by the mass, either the mass number or the mass in AMU, depending on what they give you. And then finally, what you'll do is you will add all of your answers from the previous step together. So it winds up looking something like the average atomic mass is equal to the sum of the abundances of the different isotope time the mass of those isotopes. And then you add all of them together. So let's look at a few examples. In this example, we have a data table with some information about potassium. So we have 3 isotopes, potassium 39, 40, and 41. So potassium is number 19. Its atomic number is 19. It has 19 protons. That means this isotope of potassium must have 20 neutrons. This one has 21 neutrons, and this one has 22 neutrons to get to that total mass number given. So in case they ask you about the number of neutrons. Now, to find the weighted average mass of potassium, the first thing you would do is you would change these percents to decimals. So 0.9326, 0.0001, and 0.0673. Once you've changed the percents to decimals, then you're going to multiply by the mass numbers. So you would take the 0.9326 times 39, the 0.0001 times 40, and 0.0673 times 41. And you get 36.3714, 0.004, and 2.7593. And then your last step, you would add them all together. And you get that the weighted average mass is 39.13, and we typically use AMU, our atomic mass unit. So if the sample on Earth has the same abundances as you see here, so the same percentage distribution, then this is the number that would appear on the periodic table. Another way they could give you the data from the mass spectrometer is in a graph. So this graph has relative abundance or percentage on the y-axis, and then this thing, it's m/z, but basically it's the mass number on the bottom. And I just went ahead and wrote in my estimates. So this is like about 52, and this is about 11, and this is about 17, etc. You know, as if they don't give you the exact percentages, you can estimate. You just make sure all of those percentages add up to 100. And then from there, you're going to do the same steps. So you'll change the percents to decimals, 0.52, 0.11, 0.17, 0.18, and 0.02. And then you will multiply by the masses from the x-axis there. So 90, 91, 92, 94, and 96. Go ahead and multiply. And you get 46.8, 10.01, 15.64, 16.92, and 1.92. And then you need to add them all together. And you get, when you add them all together, you get 91.29, and that's AMU, atomic mass units. Now, this particular graph didn't tell you what element it was. So this can be used to figure out the sample and the identity of the sample. So for example, once we find this average atomic mass, then you can go back to the periodic table, find the element whose atomic mass matches that number. In this case, the closest one is probably zirconium, which is Zr. Okay, so the last example shows us if they ask you to work backwards. So sometimes they could give you the overall weighted average, or you could look on the periodic table to find the weighted average. And they could give you what isotopes are present and ask you to find the percentages or the abundances of those elements. So I'm going to use X and Y to represent abundance, and then from the abundance, then we can change that back into a percent. So if we think back, you would need to take the mass of the first isotope times X, the mass of the second isotope times Y, and then add up both of those to give us our weighted average. And notice they give us an AMU instead of just using the mass number, so it's going to be a little different. If they give you the AMU, use that. If they don't, then use the mass number. Okay, so we can't solve an equation with two variables, so what we need to do is we need to create a system of equations. X and Y, we know, need to add up to 100%, or if we write that as a decimal, it would be 1. X plus Y equals 1. Or we can say that if we solve for one of them, that X is equal to 1 minus Y. And then I can take this and substitute that back into my equation. So 184.95 times 1 minus Y plus 186.96Y equals 186.21. Then you would need to distribute and solve for Y. And you would get that Y is equal to 0.627. And since X and Y are equal to 1, X plus Y equals 1, you can then solve for X, so 0.627. X is equal to 0.373, which makes sense because then they add up to 1. So I have X and Y. All I need to do is change this into percentages. So percents for X would be 37.3%, and for Y would be 62.7%. Now, this makes sense. Always think about if the number makes sense. Is it reasonable? Since our weighted average is 186.21, it makes sense that Y, or this isotope, is more abundant, greater percentage, because the weighted average is much closer to that value. So the greater abundance, the more it's affecting our average. So that makes sense. So if you have like a percentage that's really, really low, it's going to have a less of an effect, but if it's really high, it will have more of an effect. It will be closer to that value.